I'm Tim Sever. What is short circuit evaluation? Well, that's what we're going to investigate in today's video. So what to expect? We're going to give a brief introduction into what short circuit evaluation is, and to understand it in terms of the context of the examples provided, we're going to look at or examine the truth tables for and or, our two Boolean operators under consideration, or the two Boolean operators which support short circuit evaluation. I'm going to give two different examples which will flesh out the benefit of short circuit evaluation in Python. Once we provide the two examples, we will compare and contrast the two techniques and see how short circuit evaluation can be used to benefit us as coders. And finally, hopefully, we will gain a better understanding of what we learned today. So let's begin. All right, what is short circuit evaluation? Short circuit evaluation, sometimes called lazy evaluation or McCarthy evaluation after John McCarthy, deals with the way Boolean operators, which support this technique, are treated in some programming languages. Now, Python is one such language. So short circuit evaluation is a technique where the second argument, this is the right-hand argument, does not get executed or evaluated only if the first argument, which is the left-hand argument, did determine the result of the Boolean expression. So in this case, we have the two Boolean operators that we're going to consider, both of which support short circuit evaluation. We have the AND operator and the OR operator. But before we get too far into short circuit evaluation, we need to discuss these operators from both a programmatic and logic or mathematical perspective. So we know from logic that the AND operator is symmetric, so to speak. P and Q is equivalent to Q and P. In mathematics, we say the statement P and Q is equivalent to the statement Q and P, which means they have the same truth and falsity values. In programming, we would want to say that the Boolean expression P and Q is equal to Q and P. That should always be true. But is it? That, in fact, is the basis of this video, and how short circuit evaluation can get us out of trouble. So again, what is short circuit evaluation? It is a programmatic technique where the right-hand operator is only evaluated if the left-hand factor did not determine the result. And so to really understand that, we need to look at their truth tables. So here's a classical truth table for the AND operator. You can see I have P and Q. We have two Boolean variables, so there are 4 states total. They're all illustrated here. Let's notice that when P is false, the left-hand factor is false, then P and Q is definitely false, regardless of what value Q attains. Whether Q is true or false, the result is false. What short circuit evaluation says, if the left-hand argument of the AND operator is false, and that's P in this case, then there's no need to determine the truth or falsity of Q, because we know the result of the AND statement will be false. That's what I'm indicating in this table. This is really what short circuit evaluation is about. Q is never evaluated in the case that P is false. Why does this matter? Outside of simply knowing this fact, well, that's what we're here to see today. But first, before we look at our two examples, let's quickly review the truth table for the OR statement. So here is the truth table for the OR statement. Again, short circuit evaluation does work for the OR operator. So here we see that the left-hand factor of the OR function, which I've indicated in yellow here is P, when it's true, we know the result of the OR condition. P or Q will definitely be true. So in this case, the OR operator short circuits the evaluation of Q. It doesn't actually compute the status of Q. It does not determine whether Q is true or false, because there's no need. So it's very efficient in this way. So short circuit evaluation is a technique where the second argument, which means the right-hand factor, is only, that's the key here, only evaluated if the left-hand argument didn't determine the result. That is short circuit evaluation, and of course it applies to both the and or functions in Python, or any other language which supports that technique. Okay, so let's look at our first coding example. So here's a problem. Say we want to get some input from the user and we need to validate it. So here the hypothetical problem is we're going to try to validate a date format. It's a 10-character string where the first 2 characters represent the month, there's a slash, the second 2 characters represent the date, there's a slash, and the last 4 characters represent the year. So here's an example of how that can be coded, which would begin the validation of the user input. So and we're only looking at the outermost level for this example to illustrate how short-circuit evaluation can be achieved. So here we have a coding example. Please pause, review the code, and then I will run the code, and we'll see how this code segment performs. Okay, so in example 1, we have our prompt, and let's enter something that looks good. Christmas Day of 2001. And we get the result that the string passes the first test. Now remember, you saw the code a moment ago. Well, let's run it again. Let's see what happens. Now suppose we enter just 2 characters. Obviously, this should not pass our test in terms of the user input. It doesn't have the right format or structure. Look what happens. We get a runtime error. So our program failed. We had a catastrophic event happen, namely our code crashed. Let's look and see why. So here we are, back to example 1, and what we see is we entered a 2-character string. So notice I have my 2 conditions. By the way, my 2 conditions here are P is in blue and Q is in red here of the AND statement. Now remember, we get short-circuit evaluation only in the case where the left-hand factor is false. But what happens here, we have a big problem with the runtime error. Please take note that we have the user data that we've entered here on the screen. It was the 2-character sequence 1, 2, and it did not have a 5th position. So this is the part of the code which caused the program to fail. So this, you see, this is a problem. Anytime you have code that has a runtime error, that's a catastrophic problem. So let's agree that we have something wrong with this code. But before we try to look and try to fix it and see what happened, let's look at our second example. So notice example 2 is essentially the same. I have the same 2 Boolean constructs, P and Q, here, but I've switched them. Notice the length equaling 10 is on the left-hand side, and in blue, we're examining the 2 offsets on the right-hand side of the AND function. So let's look at how this code executes using the same data values. Okay, so here on example 2, we'll enter December 25th, Christmas Day, 2001 again, and everything is fine. It does have the appropriate character, at least in terms of the condition that was tested, obviously, to determine whether the string is truly in this format. We would have to do more, but that's not part of this example. Let's rerun it on our 2-character string 12. Aha! Notice we did not get a runtime error. What happened? It's in essence the same code, and that's what we're here to investigate. Okay, so here we have example 2, which is just the 2 Boolean conditions interchanged in terms of their position in the AND statement. And now notice what happens. In the event that the length of the string is highlighted in red is not 10, namely if this is false, the code never evaluates this right-hand factor. And that's what saved us. Since the length of the string was 2 in that case, this condition was false. It, being the interpreter, never evaluated this code in blue, and therefore there was never a failure at the index being out of range. So this is a great example of how we were protected from a runtime error by virtue of the short-circuit evaluation of Python. Now, of course, why did it not fail, so to speak, in the case when we had the correct date? Well, when the length is 10, we do have offsets or indices of 2 and 5 in the string, and these can be tested, right? And we should look at that with either the example 1 or example 2. If we put in a string that does not meet the criteria, you can see that the code does execute. It says the string failed to meet this first initial test. It didn't quite pass. But again, that's not really the point. The point of this was short-circuit evaluation. So what did we learn? Well, from a mathematical perspective, yes, P and Q is equivalent to Q and P. And from a programming perspective, we'd like to think that P and Q is always equal to Q and P, right? That you always get a true statement there. And in fact, it is true when both statements are defined. That means, i.e., they both have true or false values. And the problem with the failure of example 1 is the right-hand factor of Q was not defined. You got a runtime error there. And that's what the problem was in terms of example 1. So in example 2, we learn the short circuit evaluation can actually help us with coding. The right-hand factor, which potentially would have a defect in the terms of some user data that's input, was being protected from a runtime error by virtue of us checking the length condition first. If that failed, then we would in fact not have a runtime error. Why? Short circuit evaluation. The interpreter is very efficient. It didn't bother checking the truth or falsity of the statement here in blue, which is Q. So this was in fact the problem with example 1. Again, short circuit evaluation helped us. Why? We didn't have to write extra code to check to see if these offsets existed in the string. We were protected from that by short circuit evaluation. So I hope you enjoyed this video on short circuit evaluation in Python, which is one video in the Coding with Tim Sever Introduction to Python series. I hope you enjoyed this video. We'll see you next time.